This video will focus on the kinetic molecular theory as it relates to gases. Specifically, you need to know the components of the kinetic molecular theory as they relate to gas, and also how to relate it to particle motion, both in gases and liquids, not so much in solids. Okay, so the kinetic molecular theory as it applies to gases includes three different components. Okay? Again, remember, the kinetic molecular theory is just the theory that the motion of molecules affects the properties of whatever state of matter we're talking about. Okay? So the first assumption of the kinetic molecular theory as it relates to gases is that the molecules of gas are in constant linear motion. Okay, based on observation, what that means is that the gas molecules will not be turning left or right or going in spirals or doing anything crazy. Okay, they will be moving at all times and they'll be moving forward. Number two says they will only change directions if they hit another molecule or if they hit like the side of a container. Okay. So the kinetic molecular theory, which has to do with motion, we assume that the gas motion is forward, and the only time it won't be forward is if it strikes an object or another particle, in which case it may change directions. So in this simulation, you can see what it looks like, and we'll see more of these in class, but if you follow any particle, it will always be traveling straight until it knocks the side of a container and then it changes direction, or until it knocks into another particle and then it may change directions. So the kinetic motion the gases are undergoing are linear until they hit something. The last assumption of the kinetic molecular theory for gases is that we assume that all gas molecules are ideal. Okay, so they go straight unless they hit something and they're ideal. You need to understand what ideal means, though. So here it is. Number one, an ideal gas. Okay, if there are collisions between the gases, those collisions are assumed to be elastic. An elastic collision means that when the particles strike, no energy is lost or gained. It can be transferred, but you don't lose the motion energy into a different form of energy. Okay. Best example I can give to you is if you throw a ball, on the ground, it's going to bounce right back up. It's not going to like break or do something weird. An inelastic collision is a collision, oftentimes you think of like a car crash. If two cars hit each other, there's a lot of noise. A lot of times material crumples or breaks. Sometimes bumpers literally come off. Okay, those are inelastic collisions in that the motion energy is lost into other forms of energy. Sound energy, basically the motion energy is lost, right? Eventually the cars stop moving. The second definition of what it means to be ideal is that when the gas molecules hit one another, there's no attractive forces between them. Now we know every molecule has positives and negatives and that they're going to attract and repel and things like that. But the understanding is that gas molecules move so fast and are so spread out that when they hit one another, the attractive forces are negligible. Essentially, we don't have to take them into account. The last component of what it means to be ideal is that, and this is kind of a big assumption, but we take the volume of the individual particle as negligible. Okay. Gas molecules are so spread apart that the actual volume the gas particle itself takes up is insignificant to the volume that the gas contains as like a sample. Okay. So again, the three components of the kinetic molecular theory is that molecules move straight unless they hit something and that they behave in ideal fashions. And ideal fashions means they have elastic collisions. When they are around each other, they're not going to attract one another, and that basically they don't have volume, which is silly. We know that the collisions are going to lose some energy. We know that there is an attractive force, and we know they have volume. But what we find is that typical temps and pressures, which means, the atmospheric pressure, a little bit lower, a little bit higher, and then typical temps, really we're talking about a great range here. It's only if we get really hot or really cold that they don't behave in an ideal fashion. Okay, so we find these three components to be true as long as we're not dealing with the extremes. If you start to put gases under a lot of pressure, or you start to heat them up a lot or cool them down a lot, number one, they'll start getting close enough together that their intermolecular forces will attract one another, and so the attractive force thing will go away. And then the volume that the gas particle takes on itself will start to get in the way of other properties, especially if you push them close to one another. Okay. So basically from this video, all I need you to know, this is just a content-based video. What the definition is of kinetic molecular theory as it applies to gases, and basically these 5 components, the 3 components, and then part of that third one is the 3 definitions of what it means to be ideal. Okay, that's it. Do the form. I'll see you guys tomorrow.